checking those last three. And then we're going to flip over. It doesn't matter which page because your notes printed on 2 pages instead of front and back. So the back of both of them should be blank. And we're going to use that blank space to add a few things because I just want to go over when I was making your practice assignment, there's a couple things I realized that you need to be able to do that we didn't include in these notes. All of these notes on graphing are using the most basic standard form of rationals, where you have a over x minus h and then plus k. Okay, but it does get more complex. I am not going to ask you to graph anything more complex, but you should be able to understand that it does get more complex than that. And you should be able to answer some questions about more complex ones. You're not going to have to graph them, but you should be able to answer some questions about them if the graph is already given to you and things like that. Is everybody good with checking these three? Can I go on? Okay, I'm just going to get a blank page here. Just happened. Apparently I accidentally closed it. Not what I meant to do. All right, so you can just put this like on the, like I said, on the back to of any of those note pages. We're just going to add on a few things. Okay, so one thing that I want to make sure that you understand is that this is the standard form that we've been looking at. Right? I'll put that standard form. Okay, and we've only been working when we have a constant in the numerator and a linear function in the denominator. Linear meaning it's just x. It's not x squared or x cubed or any other polynomial, which it can be, but we're just working with a constant over a linear. Okay, but rational functions can get a lot more complex. They can be any polynomial over another polynomial, any ratio of polynomials. So you could have a quadratic over a cubic or whatever, any mix and match of different polynomials in the numerator and denominator. And they don't have to be in standard form. They can be in general form where you have something like this. Let's say you have a quadratic in general form down here. Now, I'm just putting a constant in the numerator, but that could be another function, another equation or expression in the numerator. Okay, it could be 5x plus 2 or 5x squared minus 9. You know, it could be anything. Okay, so this is what I want you to understand. It can be more complex and look like this. Now, the only thing I need you to be able to do with these more complex ones at this point is to still determine your domain. We still have to be able to state the domain. Now, one way definitely would be go plug it in Desmos and look at the graph and get yourself a visual. Because if you have a visual, you can see where the breaks in the domain are. Okay. But you don't have to have a graph to be able to answer this. In all of these that we were working with in standard form, remember H was the break in the domain, right? Whatever that H was our vertical asymptote at x equals h. Do y'all agree? The reason being, because if I plugged in an h here for x, what is h minus h? What's anything minus itself? H minus H, 0. Thank you. Okay, so that's why H is where the vertical asymptote is, because if you plugged it in, you would get a 0 in your denominator. And we talked about at the very beginning when we were looking at the parent functions. Let me go back to the very beginning of the notes here and show you. When we were talking about this parent function, we said the reason there is a break in the domain, the reason this asymptote is here is because X is in the denominator. And it's in the parent function, it's at 0 because X cannot be 0. You cannot divide by 0. Everybody understands that, right? If you try to divide by 0 in a calculator, you get an error. So whatever your H value is, if you were to plug that in, that's what would make your denominator 0. And you can't have a denominator of 0. So what you need to understand is that no matter how complex your denominator is, it's what would make this denominator 0. Those are the breaks or the exclusions in the domain. That's where the function does not exist, cannot exist. Okay. So when you have something more complex like this, whatever that denominator is, we need to figure out what makes the denominator equal 0. Okay, so I'm just going to focus on that denominator. Now, in the majority of cases, if it's more complex than just X minus H, you need to factor. Okay, in this case, it's a quadratic. So we're going to factor that denominator. Okay, so you may have to refresh on factoring, but X squared would factor to X times X. Okay, and since the a values here in front of the quadratic is an understood one, I just have to ask myself what multiplies to negative 15, but adds to negative 2. And if you need to do your little cross thing where you say multiplies to negative 15, but adds to negative 2 and help you organize, you can do that. So what are some factors of 15? Okay, if I do negative 3 and positive 5, will that add to negative 2? Yeah, I need the 5 to be negative and the 3 to be positive. Those will multiply to a negative 15, but add to a negative 2. So it's positive 3 and negative 5. Now, we are setting that equal to 0 and solving. Remember, you split and solve. A lot of you do not have to show the rest of this work. Once you have it factored, you can visualize what would make these factors 0. And it's negative 3 and 5, because 5 minus 5 would be 0, negative 3 plus 3 would be 0. If you don't immediately see that when it's in factored form, what you are physically doing is taking those factors and setting them equal to 0 and solving. So you end up with 5 and negative 3. But like I said, most of you can just get to this point where you have it factored and you can see, okay, a 5 would make that 0, a negative 3 would make that 0. So those are the exclusions. Okay, that's what your domain is everything except for those numbers. So those that we just came up with, those are what we call, bless you, the exclusions. That's what X cannot be, because those are the values that would make our denominator 0. So the fact that we got 2 of them, there can be more than one vertical asymptote. If you went to look at this graph, you would see this has more than one vertical asymptote. It has 2. Now, I'm not going to ask you to graph something that complex, but you need to know that it's possible. So you can have more than one vertical asymptote. Does that make sense? Now again, you can use Desmos. You could put this equation in Desmos, and let's see what that looks like actually. Okay, so it's 5 over x squared minus 2x minus 15. So you can see how this looks like it's almost going straight up here, and this looks like it's almost going straight down. There's a break right here. There's a vertical asymptote here that's at -3. And there's one here where that's happening again at 5. Does everybody see it? So it doesn't show up as a nice, pretty dashed line for you, but you can visualize where that break is happening, right? So you can use Desmos to help you with those if needed. Okay, now, the other thing that I want you to be able to answer, want you to be able to do, is not necessarily with a quadratic denominator, but just what if your denominator is still linear, but there's a coefficient in front of x, something like this. So this is still just a linear function in the denominator, but right now I cannot identify a and h accurately. If you tried to tell me a is 3 and h is -12, that's wrong. Because it's not in this format with just x. There's something in front of x. I have to get rid of that something. That's 6 in this case. So sometimes if you have a coefficient in front of your denominator, in front of your x and your denominator, you have to factor again. Okay, so when I factor that out, that's just GCF factoring. This is what I get. Y'all agree? Now, I want factored. Now I can reduce, if possible, that numerator and denominator value there. So what is 3 over 6 reduced to? 1/2. Now, that could be written like this, and then you would still have your x plus 2 in parentheses, or like you saw in some of our examples yesterday, that 1/2 is your a value. Now that it's reduced, that's your a. So you could just put 1/2 in the numerator like that, if that's how you prefer to see it. Now I can accurately identify a and h, right? What is the a value? What is the a value here? The 1/2. And what is the h value? Nope. 12 was over here. Look at it now. What's the h value? -2. We factored out the 6, the GCF of 6. So when we divided out the 6, that left us with x plus 2. Okay, that's what I'm saying. If you have to be able to factor out if there's a coefficient here, because 12 is not your h. And so if you were given an equation like this, and you're asked for where's the vertical asymptote, and you tell me at x equals -12, that's wrong. Because that would not make the denominator equal to 0, would it? If I plugged in a -12 here, that would not come out to equal a denominator of 0. So you have to factor. Y'all feel okay about that? All right, let's just try one more and make sure. Let's say I've got 8 over 2x minus 4. What am I going to, and I'm asked for where's the vertical asymptote? I can do what I did up here, and I can reduce, factor and reduce. So if I factor, what's the GCF in the denominator that I can factor out? I got to get rid of this coefficient here. So that 2. Ooh, what happened with my pen there? Hang on. So if I factor out a 2, that's going to leave me with x minus 2, won't it? Now, can I reduce this? What's 8 over 2? Okay, so that's just a 4, nothing in the denominator. So now I actually don't even need the parenthesis now since there's nothing in the denominator with it. So now could you tell me the vertical asymptote? What's my h value? 2. So it's at x equals 2. Because your h is 2. A 2 is what would make this denominator 0. Now, I said that's one way of doing it. Again, you could plug this in Desmos and look at the graph and see where's the break. That's where your vertical asymptote is, okay? Or you could do the same thing we did up here and just focus on the denominator and say, okay, set that denominator equal to 0 and solve. So I could do it that way. I could just set the denominator. If all I'm asked for is the vertical asymptote, I could just set the denominator equal to 0 and solve. And I could just do algebra to solve this. I get 2x equals 4, divide out the 2, and look at that. I get x is 2. Same thing I got over here, right? So as long as, if you understand that concept that what makes the denominator 0 is that's where your vertical asymptote is happening, that's your restriction in your domain, you'll be better off. You'll understand how to answer these questions better, and you'll understand that there's more than one way to answer these questions. You'll feel okay about those? All right, so your practice assignment is in Alex. Okay, so I want you to go log into your Alex, and I'm going to just pull this up to kind of show you why we did those add-on notes, because some of these questions, you needed that. So this first type of question here, you're given a graph and you're asked all sorts of things about it. You're asked, what are the intercepts? What's the domain and range? What are the asymptotes? Make sure that you're answering these as equations for asymptotes. Your vertical asymptote is x equals a number. Your horizontal asymptote is y equals a number. Okay, your domain and range, you're going to do an interval notation using your parentheses, and you can use the infinity and negative infinity symbols. Okay. Then what? There's that union symbol. You'll need to type in the union if there's a break. These are multiple choice down here. You're selecting what the intercept is or saying that there is none. Okay, but I just want you to have a visual of some of these types of graphs. So the graph is going to be given and you're just answering questions about it. So that's what the first couple are. Now I do want to point out something like this. These graphs look different. These are more complex. Like I told you, any polynomial ratio, anytime you have x in the denominator, that's a rational function and they can get really complex. Okay, so I'm not going to ask you to graph something like this, but if you are given the graph, you should be able to answer questions about the graph. Okay, so even though I'm not going to ask you to graph something like this, you should be able to answer where are the asymptotes, intercepts, and what's the domain and range. Okay, now I also want to point out, notice how there's this horizontal asymptote here And this middle section of the graph crosses it. It touches. Okay. Some people are saying, how is that possible? We talked about asymptotes are what we approach but never reach. Okay. Yes. End behavior. Your horizontal asymptote is guiding your end behavior. It is what the ends of the graph approach but never reach. Okay. But in the middle, it is possible to cross it. So when you get these more complex rational functions, just know that that may happen, okay? The asymptotes are guiding the end behavior of that graph, and the horizontal asymptotes are, and the vertical asymptotes are guiding in the middle, okay? So just know that that's possible. Some of the other types of questions that you're going to practice, this is what I was just practicing with you. There is a coefficient in front of X that you need to factor out before you can tell me where that asymptote is, that vertical asymptote. Or you could just take the denominator and set it equal to 0 and solve. Okay. Sometimes somebody has a preference of just factoring out that coefficient versus setting it equal to 0 and solving algebraically. So you've got a couple options there. I believe there's a couple of those to try. And then there are some where you're given the original function and they want you to make these transformations. So this is just knowing your transformation rules for a couple of those. Then that's another so 3 of those with transformation rules. Okay, and then 8 and 9 are asking you to just evaluate. Okay, so they're giving you a rational function and they're saying, this one says find h of -1. That just means plug -1 in for x. So everywhere that you see x, if it's more than one spot, you plug it in more than one spot. You plug in -1 and evaluate. So this is like in the notes when we were making the table of values and we were picking values of x. We were picking an input and checking it to see what the output was. So they're giving you the input. You're going to plug it in and check and see what's the output. So you've got a couple of those to try. And then 10 and 11 are asking for the excluded values. This is what I was explaining on the add-on notes. Your excluded values are anything that makes the denominator 0. So just take your denominator. You're just focusing on the denominator. What would make this 0? So set it equal to 0 and solve. The majority of the time, that's going to involve factoring. This one, since it's linear, doesn't technically have to be factored. You can do it just solving algebraically. Okay, same thing here. This one doesn't even require any factoring. Just you should be able to look at this and tell me what would make this denominator 0. What value would you plug in there to make the denominator 0? 5. That's it. Your answer's 5. Okay, so some of them may be easier than others. Okay, but that's what they're asking. When they ask for the excluded values, they're saying, what would make the denominator 0? Those values that you're coming up with are the exclusions. Those are the breaks in the domain, the exclusions in the domain. Does that make sense? All right, so you've got the rest of class to work on this practice. It is set to be due, let's see, today is Thursday, so it'll be due Monday. So you've got today, tomorrow, and the weekend if you need it.